Our next speaker is well known to Code Dive community, and you all know him. It's Mateusz Pusz. And he's a software architect, chief engineer, security champion with more than 15 years of experience in designing, writing, and maintaining C++ code. He does it for fun and for a living. How a lucky guy, right? And Mateusz called himself a modern C++ evangelist. And I would say this is very true because he gladly shares his knowledge as a C++ consultant, trainer, and a conference speaker as well. Mateusz Pusz is also a contributor and an active voting member of the ISO C++ committee. As a result, he can proudly say that he actually shapes the future of C++ together with the best experts, C++ experts in the world. And he is here with us today. How great is that? In his presentation, Rethinking Usage of C++ Templates, Mateusz Pusz will share his experience and thoughts he gathered during implementation of the physical units library for C++. So be ready for a really practical and summarizing presentation. And the stage is yours. One big applause for Mateusz, please.
Okay, thank you very much for this really nice and great introduction. Actually, when you were talking about me, I was looking into me like there, and I was growing on this wall. Yeah, thank you very much. My name is Mateusz Pusz. I'm the chief software engineer and ISO C++ committee member, trainer, consultant. You can find me on the conferences like this one or others. Today we'll be talking about my thoughts and some feedback from my recent work for the library of physical units library I'm working right now that hopefully will be a part of C++ in the future. And today we'll be speaking mostly about templates and how we use them and how we can use them in the future. We'll address today 3 different areas here. We'll talk about user experience, we'll talk about new toys that we got for C++ templates in C++20 and possibly in the future, and also about performance. How can we optimize compile time performance, because runtime performance we know it's really nice here. So, user experience. To talk about user experience, in my case, I have to introduce a bit the domain. The domain is the physical units library. So basically, this is a library similar to std.chrono, like std.chrono duration, that allows us to scale units, like length, like convert units, or do dimensional conversions. So you can convert from length, time to velocity, and do different dimensions calculations here. So let's take a simple toy example for the use case today. This is average speed. It takes distance, it takes duration, it divides it, and returns velocity. I don't care right now what's the syntax. We'll compare a few different libraries, how they provide this facility by themselves. As a use case, I would like, as a European guy, I would like to provide kilometers and hours and get the results in kilometers per hours with just division of those values without any intermediate conversions. But also, I know that there are some people that are using different units, and this covers the other part of the world, in US, for example. So you can provide miles, you can provide hours, and you get miles per hour also without any intermediate conversions, just division of those two. This is how this library should work. It should provide compile time safety. It should provide many units with different prefixes. There should be no runtime overhead. It should be as fast or even faster than working on double types. So this is how you can do this with boost units that's on the market for many, many years. It looks quite nice. You take the length and time here, and you get out the velocity from it. And thanks to usage of template aliases, because all of those like velocity, length, time, and so on are template aliases, this looks really nice for the developer, yes? It's really convenient to work with. However, if you make an error in the calculation, like here, yes, the division, the multiplication of length and time will not produce the velocity. There is no chance to do it. You will get a compile time error. And it will look like this one. And please note all of those 3 dots at the end of the screen, because this is not the end, and this is only the first line with a type of the error. This is the rest of the line. This is only the first line of the error log, yes? This is how it looks, because aliases are lost quickly in the translation or compilation process. So developer has a really nice environment to work with, user not so much. But you say that GCC maybe is not the best compilers. There are compilers that provide shorter warnings. So let's try, for example, Clang. This is the output from Clang. It's shorter, but can you tell more about what's the problem here? So I would say that problem is not that the error is long. The problem is that it doesn't provide information we need. I can deal with long errors as long as I can understand it, yes? This one is really short, but still I don't understand what's the problem here. Some 1 minus 1 difference, and we don't know exactly what's the problem here. And this is another library from Nick Holthaus. I just want to show it because it provides similar user experience from the developer's point of view, but actually it's using static asserts for error verification. So with static assert, you get something like this. Units are not compatible. And you have some information about trait being used here. But actually, if you imagine that there are more calculations here, not only this one, then you don't know what's unit from, unit to. If there's only one, you can find a stack trace of functions, and you know that this is unit from, this is unit to, or whatever. But if you have like 10 intermediate calculations in the function, and the last one is wrong, it's really hard to know what's the problem here. So static asserts are not the best for user experience here. However, Clang, this time, provides better user experience here, because it actually prints what was the type trait that failed. But still, do you know what the problem is? Even do you have context? It's not that easy to analyze, because every dimension here is a separate parameter of the primary template. And you have to know that this is length, this is probably mass, and this probably is time. So this is probably a velocity. But you have to know the design, and you have to calculate this all of the time by yourself. So finding the difference between power or energy will be really hard here. So for most template metaprogramming libraries, compile time errors are rare. It's hard to break, for example, std vector or string to have bad error logs from it, because you used it in a wrong way. But actually, for this library, and possibly for some other libraries, the only purpose to create it is to generate those errors many times a day for an engineer. So we should rethink how we deliver user experience for such an engineers, because in most cases, users of those are not C++ experts. They are just engineers or scientists working with this as a tool. So they don't know much about templates, they don't know much about those errors. They would like to have user-friendlier environment to work with. So this is the title of this talk. For such use cases, we have to rethink how we do templates to provide better user experience for our users. But user experience is not only about compilation, it's also about debugging. If you put a breakpoint here, actually there is no error here. This is what my IDE, namely CLion, prints me. Here we see that these are actually different types, but CLion gets lost with those long aliases and prints exactly that's unit of double, unit of double. The same type. Looks strange. So I go to GDB. This is a breakpoint. Do you know what are the types that came to this breakpoint? And we want to debug in a nice environment too. Not only compilation errors are a factor here. Actually, it's even not that bad, because in breakpoint here, the default parameters are omitted. But if you type something like p-type, this is only p-type of one argument of boost units. This is a long one. So As a developer, probably you cannot imagine living without aliases. Living without them, without aliases, without type devs, would be insanely hard for us as developers. But this is what actually our users face every day. And we have to think about alternatives for this. Aliases are quickly lost in the compilation process. As a result, as you've seen, the errors are really hard for the end user. And yeah, it's a pity that we still don't have the strong type devs in the language. The first proposals about this probably started like 10 years ago, and until now we couldn't agree how to do it in a right way. Because actually it's really hard to do it correctly for all of the use cases. So what we can do with it? We can use inheritance as a workaround. So instead of doing an alias here, we can just inherit from some other class, our primary template instantiation, to be specific. So similarly to strong type devs, as those types will not vanish in the compilation process, will stay there forever, yes? And what's also fine is that if you have like operator plus taking this base class of primary template instantiation, it will also work with the child class because of the inheritance process, yes? You can always pass the derived class to a base class pointer or reference. Alternatively, strong type devs, those will never inherit things like constructors or assignment operators. You'll have to retype them or import them to the scope by hand. Also, if you have things like operator plus returning something from 2 parameters, this something will be still a base class rather than the child class. So you have to somehow deal with it. So this is not the ideal solution, but it somehow works. It's a good fit for empty types like dimension, unit, so tag types mostly, because for something that has a lot of interface, a lot of constructors, you'll have to basically rewrite it every time, so it's not efficient. But for short tag types like here, it's a good solution, and it somehow works. However, we have an issue here. When we have this simple velocity equation, we have here length and time. We have operator divide in a quantity type that takes here the length and time, and it has to produce a new quantity that will be velocity. So basically, it will create a new primary template instantiation, saying that there is a length to exponent 1 and time to exponent -1, because this is velocity. But actually, it will not be able to produce the child velocity from this primary template instantiation of the base class. Because how to do it automatically? Yes, there is no language support for it. So for this, I introduced a feature called downcasting. And this is downcasting version 1.0 that I presented actually on CPPCon 2 months ago. For every inheritance like this one, I hate it, and I have to provide a type trait specialization, saying if you find base type of this, so this long primary template instantiation, just move to the child class. So every time you see primary template instantiation, get the nice class that the user defined for it. It can be only one-to-one relationship, yes? For one instantiation, you have one strong type. And I had to do it for every dimension, every unit in the library. And it was a problem for me from the very beginning, but I couldn't find a better solution. However, I sit with Richard Smith on CPPCon after my talk, and we found a solution for it. So this is actually the version 1. You have just an inheritance of primary template instantiation to a strong type dev. With new design, you provide 2 helpers here, one between those two, another one here. This one uses CRTP idiom, so curiously recurring template parameter idiom, that takes this type, provides it as a first parameter of the child class, base class, sorry, and then provides the type that should be used as a base class for this one. So basically, we inherit from this type, yes? And this type inherits from something called downcast base that basically provides the facility for downcasting. So how it looks? Downcast base takes this base type, so this unit of length 1, let's say. It stores it here and provides friend function downcast guide that takes the type of this class has an auto return type, and this is only a declaration, no implementation, because we don't know in this place what should be the child class that we want to convert to. But we have to provide it here because this is what engine will see, because this is what it will construct from the blocks like length and time. Then we have some concept that basically verifies if it's downcast stable. It's downcast stable when it has a base type, and actually when it's derived from downcast base, so this class of the base type. And you have this downcast child. Downcast child takes the target, so the child class, and it implements this function declared here with return, saying we are returning a target. With this, we implemented here a function that we cannot call here because it's so-called hidden friend, so we cannot call this function from here. But this function actually is called from here, but here we don't know how to implement this. That's why you had to split it to two different parts in the inheritance hierarchy. And this is why auto here is really important, because this auto is only known here when we return something. And it works. So one last thing is how to actually you can do the downcast. So the downcast is a helper for the engine. It's an alias here. And you have some downcast target implementation here. Downcast target implementation checks if it has a downcast, then you're doing downcast guide function with instantiation of this type and take the kill type of it. Otherwise, you just return the type. So this long primary template instantiation. To know what has downcast, you can implement this way with concepts saying that it has downcast if this expression is well formed. So there is a downcast guide that takes this as an argument. And that's all. With this, you can implement a unit as a downcast base of unit, then have something called, for example, named coherent derived unit as a downcast child of this child, and then implement meter, for example, as meter here. So user even do not have to see this downcast facility. It just have to obey to CRTP idiom. And then, in, for example, multiplication operator, you use this downcast function to downcast the result of multiplication to a strong type provided by the user. So instead of having this long alias, we have here exactly the type provided by the user. So, for example, meter per second. So this is actually result from my library for aliases. You can see that even with aliases, it's not that bad as with other examples we've seen. It's not that long. But this is with downcasting. This is a breakpoint of function average speed that takes quantity of kilometers and expressed in doubles and quantity of units of hour expressed in double. And I would say that this is user experience that users would like to see in this library. And this is implementable. You can use this downcast facility for any things you would like to have for strong typing. It works pretty nice. But please remember that this is only for like simple types that do not have many constructor, many assignment operators, because for those, it's not that convenient. Also, talking about the debugger, right now the debugger also provides the information like quantity, kilometer double, quantity, hour double, or breakpoint looks like this one, and p-type. It just works. So let's move to the new toys that we have in our toolbox. First part will be non-type template parameters because those changed a lot in C++20. And actually, they changed a lot 2 weeks ago in Belfast. So we'll be talking about the latest changes from the last ISO meeting. Let's talk about the ratio. Ratio is one of the main tools that serve to implement chrono duration, yes? Ratio is implemented as a primary template, class template, that takes just nominator and denominator as two integers, and this is a type kind of template parameter. It takes, it has here numerator, denominator, and finds GCD of those, and stores the type. And actually, this static sign, static GCD, static ABS, in most implementations we have right now are again class templates. So this is one class template. There's another class template. And there is one more class template that actually uses more class templates. So every usage of ratio provides many instantiations of class templates. And we will learn in the performance section, instantiation of the class templates is slow in compile time, because each of them requires the compiler to do the dynamic mode allocation, which is not too fast. You can implement, one more thing. There is also some things like ratio multiply. Ratio multiply, is a function, utility function that allows us to multiply ratios. There are more functions like divide, add, subtract, and maybe some more there. And they're, again, using another class templates to implement the functionality. You can implement the same functionality for class template using context functions that actually you have in the library. We have std.gcd. You can implement your own ABS because there is no compile context ABS for now. And with this, you have better reuse of the runtime code, less template instantiations, because you're using simple context functions. And the same for this ratio multiply, you can just use functions instead of other class templates. And you will learn later on that's much faster than the previous case. However, with C++20, you will have non-type template parameters extended. This is a new definition that was formed about 2 weeks ago. Right now, in C++20, non-type template parameter has to be a structural type, or a type that contains a placeholder, so an auto, or a placeholder, so basically CTAT type. The parameters will be deduced. And what does structural type means? Structural type is a scalar with a constant destruction, so it has to provide constant destruction. It can be an L-value reference or a literal class, where all of the base classes and non-static data members are public and non-mutable structural types. So basically the same as those. And how to say that two instantiations of NTTPs are the same? Basically, there's a new term defined called template argument equivalent. So they have to be template argument equivalent in order to create the same instantiation. And what does it mean? It means that they have to store either integral types, enumerations, null pointer t. Those we know already from the language we have for many years. But here are coming some new things. Floating point will be able to use in class templates or function templates as a parameter. We will be able to use pointer types, references, pointer to member, but this is what we could actually use up until now. But again, we'll be able to use arrays. We'll be able to use classes with all of the sub-objects being also template argument equivalent. We'll be also even able to use unions in templates, which give us a lot of new possibilities to use this feature in the language. So let's re-implement ratio as not a class type, not a template type at all. It's just a class. It has nominator as member, not template parameters, and just a constructor that does exactly the same that the stud ratio was doing to initialize the types inside. Actually, this probably is not needed by the latest definition. I just probably should remove it. And this is actually ratio multiply, just operator star. And actually, you can really easy write also operator star that takes not only the ratio, but also literals here, values. And you can provide this all the same for division, addition, and subtraction. So what's the difference? To do it with a type, I have to write something like this. That, for example, foot is ratio multiply ratio 1/3 of yard. Right now, I can just work with values, saying that this is yard ratio divided by 3. If something represents a value, let's say concept, NTTP is a better usage for it rather than a class type. Also notice this one. These are also NTTPs in those definitions. Providing a string, you'll be able to instantiate a template with a string. this is also NTTP. So this is how, for example, how division operator can look in this library. It has a long ratio divide here. And this is how it can look after the change. Also, you can say that your dimension maybe should be a value. And then you have just division of dimensions here and division of ratios. And this one looks much easier than this one above. These are the new possibilities that you have from class types in non-type level parameters. So I would say that maybe class types in non-type level parameters will be one of the most or the biggest changes we observe for template metaprogramming in last decade. They will change a lot of code we write right now and the way we are doing this right now. Think about what you can do in templates with floats, with units, with classes. It opens a new doors to many things. Next chapter, concepts. How do you like this interface? Great, yes, we are laughing from it. This is C-like interface, right? We don't know anything about it. Is this one better? And actually, with C++20, you will be able to write it this way. Is it much different? Or this one? Yeah, one of them will fail in runtime, one of them will fail in compile time. But if you while you're reading like cppreference.com or you are going to, I don't know, the Oxygen documentation, do you see a difference here? I don't know what should be provided there in any case. Or this one. I would say that unconstrained template parameters are the void pointer of C++. And I'm fighting with this and actually believing in this one actually made my library, I believe, much better. And I saved a lot of time in debugging or trying to find out why my concepts or my templates doesn't compile, for example. So what are concepts? Class, functions, variables, aliases, all templates of those can be constrained with some requirements. So those are put on the parameters of the template, and named set of those requirements are called concepts. So concepts basically are named predicates that are evaluated at compile time, and they are a part of the interface of a template. So when you're looking for the documentation, you see what's the interface of it. So this is, for example, way better than static assert that is just quality of implementation rather than the part of the interface. But I observe some problems with concepts usage or introducing new concepts to the language. There is a statement by Eric Niebler that wrote the range v3 library and has probably the most experience with concepts right now in the industry, that says that even though concepts are constrained on types, they should be found while looking on or studying the algorithms. But some of my friends say, or oversimplify this, saying that all concepts should arise from algorithms. Because this is what Eric Niebler said, yes? I don't believe that Eric said exactly this, but this is how it's perceived and used in the industry. But I would say we think about this because this is what we explored so far. Do you know what the map presents here? This is world, yes? Maybe I will rotate it upside down. Does it look better? Does it look like our current understanding of how geography looks? Probably not, yes? And I would say this is our state of concepts right now. We're still exploring new areas here, and we still are experimenting with new things. We agreed in the committee that we have 3 categories of concepts. predicates that basically are named ending with preposition, like derived from. We have capabilities, like swappable, named with adjectives, mostly finished with able or able. And abstractions, named using very generic nouns. And we agree that we have those three categories of concepts. And some of us think that this is a closed set. But I would say that world is bigger, yes? Then we can maybe imagine right now we have to explore new ideas. What about our ratio multiply that takes just two type names here? I can instantiate it this way. Why not? This is what interface allows me to do. And this is what I get, yes? And this actually is an error deep in the library implementation. Somewhere something failed, yes? In the library implementation. Does it mean that the library has a bug? Or I just instantiated the type with bad types, right? I don't know if I should submit a bug or is it my issue. So I would say that there is maybe a new concept category called family of instantiations. I would like to have ratio concept saying that it's just a type trait, it's ratio of t. And this is a simple type, really simple type trait to write. Actually, this is based on variable templates. So you have is ratio by default false, and if you have an instance of ratio and a number denominator, you have true. It can be named with an uppercase first letter of the class template too much, but I know that it will not gonna fly in the committee. Actually, finding a name for this will be hard, because if you have ratio and ratio, how to find a good name for one of the other? So bike shading will be the hardest problem here, to find good names for those. But I believe this is the fourth category we are missing right now. Another perception issue I found is that many people say that defining a concept is hard. So you should limit the number just to not make too many errors. I think that's a problem because, again, we only explored this short area of C++, and also because it's a new feature, and we are afraid of many new features. So again, I would like to show you a few simple concepts that are really, really easy to prove they are right. So this is a type trait that we've seen, yes? And this is a concept. Can it be implemented in a bad way? So is this concept easy to prove correct? This is not a hard concept to write, yes? Or if you decide that ratio actually is not an instance, ratio multiply with this one. So you have this concept ratio right now, and right now if you have the same error, string and milli, we just have the source problems here, so we know that we cannot just try to instantiate this template because it doesn't meet predicate, saying that basically is ratio in concept ratio evaluated to false for type like this one. So it didn't try to instantiate the template, it just said that you provided me a stupid type. If you don't like instantiations of specific ratio type, you may say that it's ratio-like. It just has to provide you two members, nominator, denominator. And again, is this concept hard to prove right? It's a simple concept, right? And making those, again, simplifies the analysis, makes the interfaces, saying what I actually expect in this utility. Or maybe do something like this. If you don't want to name concept everyone for every type, because then we end up like hundreds of concepts, you may create a concept called satisfies that takes any type trait and calls a value on it. Is this concept easy to prove correct? That's a really simple concept, right? But now you can use it in this way. So you can say, where I have this one. This is type rate, this is here. Satisfies its ratio, satisfies its ratio. So you don't have to provide many named concepts. You have only one called satisfies, and provide a type rate. So this type rate actually has to be implemented in terms of class templates rather than the template variables, because it has to have this value member provided by this true type. And again, we have really nice error log from that. And the interface in the documentation specifies exactly what's expected. So with this, you can implement functions like calculate fine when you were driving too fast with your car. It takes velocity and the velocity concept, and on the velocity context basically is a quantity of velocity. Quantity of is we have to provide type t, that's quantity, d that's the dimension, and basically the dimension has to be the same for the quantity and the dimension you specified. Dimension in my library has to be an empty type, and it has to be something inherited from the downcast base. And quantities again is quantity type rate. And we are using here this is dimension type rate that you've seen on previous slides. So these are family of instantiations, but they make all of the interfaces really strong. You know what is required for this function? Because this is a template actually, yes? This is generic function in C++20. Every time you see auto, starting from C++20, it's a template. It's the same like with generic lambdas from C++14. Concepts are not just a syntactic sugar for enable if or void t. And some people believe that that's the only use case. You can easily constrain function return types with concepts. Try to do this easily with enable if, for example. It's not that easy. You can constrain function stack variables with concepts, saying this average speed returns something, I get auto, but auto has to meet velocity concept. You can also constrain classes, primary classes, class templates here, without introduction of any additional parameters, because you can do sphere on classes, but then you have to provide more parameters that will be used for this sphere. And you know what? The earth is round. There's more things that we can explore. What are template parameter kinds we know right now? We have types, we have non-types, and you have templates, so generators that you can provide to template functions or classes. If you want to write something really generic, you don't have a placeholder for all of three of those. You have to say either type name 3 dots, which will always point to this one, or auto 3 dots, which will point to this one, but you cannot say I have any parameter of the template here. What if we would introduce a universal template parameter kind? And for example, with such syntax, you will be saying, this is a primary class template. I don't care what are the parameter types here. I just want to state here that that's a class template. And what we can do with this one? For example, you can write something like this. Instance of, provided this is a template parameter, but basically it takes any kinds of parameters here. If it actually instantiates the same stuff, it's true. So now you can define concept is that will be using this type rate. And with this, you can write is to ratio. And you don't have to write those type rate is ratio, is duration, is quantity, is whatever, and more. Just this one definition will cover all of the cases. And simple concept like is with this feature will allow us to match any template definition, no matter what are the types and number of parameters there. Yes, Jason?
Is that feature accepted currently, or is this
No, the question is if this feature is accepted currently. No, it's not accepted, but there is the paper that will be submitted probably for PRAC. If you want to contribute or you have some use cases for this, and I know that many people are, then please let me or other folks know about it. Because we are right now looking for use cases. We have at least 3 use cases that are different and really, really powerful to show to the committee. I believe that it will simplify many, many things. Just because we have not much time here today, I will just show you this one use case, but there are more. And with this, again, we have really nice error logs and really strong interfaces, and you don't have to provide many named concepts for this. You just say is provided template, because this is template. Yes, this is not a type yet. It was not instantiated. So you say this is an instantiation of ratio. I don't care what is instantiation. I just want to make sure that it's a ratio. So what are the benefits of using C++ concepts? First of all, they clearly state the design intent. So the architect of the interface can communicate really easily the intention to the user. They're like contracts, but in compile time. They are embedded in a template signature. So in all of the documentation, you will see this. cppreference.com, Doxygen, whatever. They simplify and extend SFINE, so substitution failure is not an error. So you can, you can use enable if for disabling specific overloads. You can use things like tag dispatch to select the best overload. You can use void t to query for member types and functions in a type. But with concepts, you can do all of this much easier. And you can actually do more, yes, as we've seen, because of those constraining of function return types, constraining of stack variables, class templates, and so on. And they greatly improved error messages. Compile errors are much better, and they are generated before the template is instantiated, so the user exactly knows what's the problem. So the last chapter for today, performance. For compile time performance, there is a tool written by this guy. This is Louis Dion. He written Boost HANA some time ago. And it's really, and basically this young guy changed the industry a few years ago when talking about template metaprogramming stuff. He showed new ways to use it, and we started to use it in production. Right now, probably the same is done by Hanna Dosikowa from Czech Republic, providing us how to write the regular expression libraries in compile time. So it seems that Hanna is a privileged word in changing the metaprogramming word in C++. But Louis created this meta bench. You can find it on GitHub. It's for free. It's basically CMake module that simplifies micro-benchmarking. You can not only benchmark all of the file, but precise part of the files with this one. And also there is a web page called MetaBench, where you can compare performance of several MPL algorithms implemented by different libraries, by different authors. This is how you can use it. This is CMake. You say just, this is a data set called in this way. This is the input parameters, like for the x-axis of the graph. This is its name. And you're doing the same for other data sets for different implementations. So we'll compare the stud ratio with context, and ratio with NTTP usage. And then you define a chart, saying that you want to have a chart of those 3 data sets. To implement a test, you are using Ruby. There is a loop here. There is some structure that has a ratio. One here. This is used when MetaBench is enabled. This one is when it's not. So we are not comparing what's the performance of adding a new parameter to a structure. We are only analyzing what's the cost of instantiating the ratio here. Because in both cases, we are adding this same member to a class. And this is how the outcome looks. This is for stud ratio. This can look for the NTTP ratio. And these are the results. This is typical stud ratio implementation in our libraries. As I said, all of the stud ratio implementations right now are using those class templates to calculate ABS, GCD, and all other things. If we used consexp, so the orange line, we could have this right now. But it would work only from C++14 up. So that's why it's not there, because the developers want to have standard library to work with C++11 too, yes? But the performance difference is really, really huge between consexp usage here and class templates. And this is NTTP for this case. This is 1 multiply and one divide on a ratio. However, NTTP is not always the fastest one. When we look only on the creation of the ratio, actually NTTP is really slow because abstract tree that compiler has to generate for a constructor, it's way more complicated than just instantiation of those types here. But compare this to the performance, it's only for the same number of samples, it's only 2.5 seconds here in the worst case, and it was 42 here, yes? So we still win with NTTP, but when you will be doing something that is non-trivial for some classes, then consexp is actually not fast. And this is exactly what Hannah said on C++ Now this year. Concepts are really slow. For her use case, in the regular expression library, GCC 9 took 2 minutes, Clang was better, but this was PHP, right? So our compilers has a lot of room to improve. We are trying to force our compiler vendors to use some on-the-fly compilation of our code, just to compile all of this and use a binary rather than abstract syntax tree. So we'll be jitting C++ code during compilation for consexp functions, maybe at some point. Rule of Chiel. I've learned about this for the first time 2 years ago from Odenholms, here on CodeDive. Childus was the intern of Odenholms, and he he approached the template performance from other direction than all other guys. He just didn't measure. He wanted to prove it from a mathematical point of view, find what are the different constraints here and steps that basically influence the performance. So what they found out? The fastest is looking up a memoized type in the compiler. Then adding a parameter to an alias call. Adding a parameter to a type. Calling an alias. Instantiating a class. Instantiating a function template. And doing sphere. This is why this stud ratio typical implementation is so slow, because it instantiates a lot of class templates. And we could improve our type traits. For example, this is typical implementation of the conditional we have in the library. It's the class template. It uses bool here and has true and false types that are used either for true case or false case. And we have an alias as a helper here. We could re-implement this one in a bit more complicated way, providing class template saying this is only a bool. So this is when it's false, we are using false. And this is when it's true, we are using true. And this actually has alias template here that has true and false. So with this approach, we always ever have only 2 class template instantiations, one for true, one for false. Because this is the most expensive thing we can do. And then we are just adding new type aliases to those two classes. And class aliases, as you've seen here, are cheaper than instantiating a new class every time. Because here you can have to instantiate every time a new class for every check. How it proves? This is stud conditional. This is stud conditional with an alias. And this is stud conditional when you are trying to not use this alias, but just use this one directly, which is not convenient because you have to use here this template disambiguator. But this alias also costs additional performance here. All of the aliases, those _v, _t, _v actually are variable templates. They have to be instantiated, and _t is an alias. All of those helpers also cost you the performance of compile time. But they're really handy to use. It's up to you to decide if you want to have performance or easy to use code, easy to write code. Every instantiation takes its part in the performance. The same is in Clang, so compilers are pretty consistent here. And let's look on the one more example, because this is something that was not covered by the Rule of Chiel, because they didn't measure what's the performance of the variable templates. This is our typical implementation of isSame using class templates. And you can implement the same with variable templates. You can partially specialize variable templates too, like classes. And then you actually don't need to have this additional helper here, because you're already dealing variable template here. And with this, here are the results. This is stud is same with a helper. This is stud is same without the helper. And this is same using variable template for GCC and Clang. What about concepts? Yeah, we spoke a lot about concepts today. From my experience, concepts are really not that expensive at compile time as they could seem so. This is not actually release finite. There are also some memoization being done there. I also found out that you can improve the performance of compile time for concepts is when actually you don't use concepts everywhere. You're using concepts in the user interface, like here, exponent of dimension, for example. The dimension takes a parameter as an exponent. But every time then, when you're using here the implementation, you don't have to put exponent again here, because there is no other way. There cannot be any other type here, because this type had to be already created, so this check already happened. So you don't have to repeat exponent here every time, because it already instantiated this class, so this check was done. Also, when you're providing like a user interface here for dimension divide, then you have the detail. You may probably also think about skipping this check again here, because this is implementation detail. User should not use this one. And this is the only usage of this function, so you can prove it right easily. So with this, you don't pay for concepts everywhere. So basically, my statement, every type name t should be removed. Maybe not, it's not that true here, but I would say every type name t in the user interface should be removed from your code. This is the measurement I did with concepts, without concepts, and with concepts with only user interface. As you can see, the results are not that different. Of course, concepts always will be slower, yes, but this is something you are using. This is not, we are not, there's basically, as C++ states that we are not paying for what we are not using, yes? But here you are using this stuff, and it has a lot of benefits. So you have to pay a bit for it. But it's not a huge factor, as you can see. At least from my measurements, because every measurement can differ, of course, yes? Every use case is different. This is what I measured from my library. If you want to find more about template metaprogramming, about different practices to write fast compile time code, go there to MetaBench. They're comparing different stuff. For example, you can see the comparison of this is what? This is stud sort? Probably yes. Yeah, this is sort in different libraries. Bridgend, Quasir, Meta. Actually, Quasir written by Odin is the fastest one for nearly every test. So there is more than one way to do it. To provide the same feature in compile time, have the same performance in runtime, but every way of doing this may have different compile time performance. And we should be aware of it and also try to optimize it, because we know more right now that we knew like 10 years ago. Try to use aliases, try to use variable templates, try to limit the instantiations of the class templates, because those are slow. Also remember that if you'll be using NTTPs with some non-trivial context functions, those will be basically interpreted by the compiler, and this interpreter is not fast for now. Takeaways from the Rethinking C++ templates talk. When you're designing a template metaprogramming class, think about the user interface. Think about their experience. Developer's experience is not only the factor that you should use here. Yes, there are some techniques that I've shown you today that actually improve user's experience a lot. I hope that maybe I will be allowed to standardize those downcasting traits, so basically everyone will be able to use them. And then maybe some libraries will be easier to use. Use C++ concepts to express compile-time contracts, to improve your productivity, to improve compile-time errors. Use non-type parameters in case your template parameter actually represents a value rather than a type. And optimize compile-time performance. Use MetaBench or other tools to check the performance of your library. As I said, there are more than one way to do it. Try to find the fastest way to do it, because it's one of the points that our users complain the most: the performance of C++ compilation process. But actually, templates are not the slowest one there. Overload resolution is, and for those, actually, you can save a lot using hidden friends feature. But this is another subject for another talk. And with this, we are moving to questions. We have 3 minutes.
I have a question.
Sure.
Can you go back to the diagram comparing the ratios creation performance?
Mm-hmm.
The previous.
Yes,
No, this one. This is conditional. Ratio. I need ratio.
Ratio. It was previously about
This is
it the
same.
same?
This is conditional. I need ratio.
Okay, ratio. Ratio will be
There are 90
the
slides here.
next one, yes.
this one or this one?
This one.
Okay.
I am curious about this fluctuation in the graph. I was wondering whether how it happened that with the increment of elements created, the compilation time actually reduced instead of rising gradually. Is it maybe a margin of error, or?
So the question is regarding this start here, yes?
Starting, then it grows the compilation time, then for ratio context,
I would say it's mostly about measurement error probably.
Yeah.
Because every process has to start at some point, and the performance of starting a process probably is not deterministic in the system. So this is the measurement error here.
Okay.
It will not be consistent probably, and actually it's really hard to implement. You see, this one is actually less stable than for example, those graphs.
Mm-hmm.
Even though the number of samples was exactly the same. When you are measuring something that takes 2 seconds and your launch or part of the second, basically the environment makes a difference here.
Mm-hmm.
I could improve the number of items here, but I wanted to show the same scale for both graphs. Mm-hmm. Otherwise, I would just, instead of 10,000, I would use like 100,000 to make it stable.
Okay,
right?
Thank you.
Okay, who has the question to Mateusz? Could you please a little bit? And if any of you have the question in your mind already, please come here, because that we can have more questions in the time we have left.
Yes, thank you for talk. And I have a question related to template equality.
Mm-hmm.
I have this new term what was discussed 2 weeks ago, as you said.
Mm-hmm.
And the question is, what about the arithmetic expression as a type parameter? template parameters. Are they evaluated before they used, or they may be different? So 2 multiply 3 is different from 3 multiply 2 and different from 6.
You will use a result of those rather than the equation itself. You will use a result of the equation so it will use the instantiation. So you mean 2 multiply 3 might yield a different result than 3 multiply 2, but for integers or some smart type?
For integers, just arithmetic.
So they will provide the same value, yes, as an outcome, and this value will be used for instantiation. So basically, we'll end up with the same instantiation.
Okay, good, thank you.
But you may imagine some strong types that behave differently. This is a power of C++. You can overload operator plus and do some magic there.
Okay, who's next? Seriously, no questions for such a talk? Come on. Okay, I have some volunteer. Great.
Yeah,
Don't
I
be shy.
would like to ask about another issue with templates. I mean, because this is compile time, and another issue for me is the size of the binary when you compile with debug. So it can be hundreds of megabytes in the debug. So for some embedded application, it can be not applicable.
Yes, so this is some concern here, yes, but are you comparing to what? To using plain doubles? Then of course you have more types here, but if you would like to write the same code, the same functionality without templates, but just with strong classes, you'll have the same binary size because you have the same number of classes there, yes?
No, I mean, for instance, if you have the boost for state machine, so there are many subclasses under the hood, and all of them are removed during optimization, but in the debug they are in the code, and the code is really huge.
Yeah, I understand what's the issue here. The problem is that for debugging purposes, you would really like to have all of the code there because otherwise there will be really hard to debug it. I mean that, for example, you can imagine working with doubles for units or having a strong type for units. Of course, in this case, you have more types and more breakpoints or maybe like more steps to do in the debugger to go for the calculation because there are strong types in the meantime. I mean, that's not a problem with types, the templates, it's a problem with strong types. Because if you would like to do it without templates, you will have to provide all of those types by yourself. And then your binary will be the same size. So either you're using strong types and then you pay for strong types, or you're using doubles, and then you have small binaries, but a lot of problems. It's not a problem of templates, it's a problem just of strong types, in my opinion.
I mean, you can also say the same for the compilation time, so that we anyway need this, yeah. But
Yep.
If this is, for instance, something like a problem with elf and huge dwarf information, you can extract the dwarf, prepare more or less stripped elf, put it on the device, and debug it remotely with the symbols on the PC.
Yeah, so the comment is here that you can play with some binaries elf image size and image here and basically divide those to different places and have it smaller. But as I said, it's not a problem of templates. This is a problem of using just a strong type.
Yeah.
okay.
Okay. Anyone else? Because I guess that would be our last question. Anyone?
Okay.
Okay.
Thank you
then
very much.
Thank you very much, Mateusz, and big applause.